In our previous video, we talked about stress and strain as tensors. And today, in this video, I want to amplify that point of view and talk about how do we relate and couple stress and strain. So we've talked again about stress as being important for causing deformation and strain being the response to deformation. And I'd like always to point out that when we're talking about, as we are today, talking about deformation of solid materials, that fluids also have the same response, although fluids, of course, also flow as well as respond elastically. So the question today, again, is going to be, how do we relate stress to strain? Now we have two tensors, second-rank tensors. They're both composed of 9 components. We want to know, how do we go from one to the other? So we're going to take an approximation. We're going to assume that the linkage between stress and strain is linear. It doesn't have to be. There's some interesting examples where that's not the case, and one that I'll use later in class. And I won't focus on this, but I'm going to look at stretching a piece of rubber, such as this. And that is not a linear relationship. The amount of strain I get is not linearly related to the amount of stress. But in the Earth, almost always, there is a linear relationship between stress and strain. So here I sit with two tensors, and I want to know if I apply a stress, what's the amount of strain that I get? Or if I have a strain, how does it relate back to the stress components? And again, we're going to use a Cartesian coordinate system off here in the lower right-hand corner. And I want to ask, if I want to know how much strain I get, epsilon 1, 1, it's determined by all the stresses, all 9 components of stresses. And likewise, if I want to know something about sigma 1, 1, it's determined by all the strain components in the strain tensor. And how do I make this coupling? How do I go from stresses to strains or from strains to stresses? So the simplest way to do it, you can just take the brute force approach and say, I'm going to express all of my strain terms, epsilon ij, in terms of all of my stress terms, which I'll call sigma kl. And again, the k and the l and the I and the j simply refer back to my Cartesian coordinate system, x1, x2, and x3. And if I now look at the strain terms being dictated by all 9 of the stress components in the stress tensor, then I need some term that goes in between, and it's going to be this term I've written out as S, which is going to be called the compliance tensor. And if I go from strains and want to calculate stresses, the tensor I have in between is called the compliance, or the stiffness tensor, denoted by C. And we'll return to those and define them more clearly in just a moment. So now I have 9 components in my stress tensor, and I want to calculate 1 component in my strain tensor. And the way I do it is I need to sum up, for example, if I took epsilon 1, 2, it's determined by sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, etc., all the way out to sigma 3, 3. And the S components, or the compliance components that go in between, are S1, 2, 1, 1, S1, 2, 1, 2, etc. And the subscripts come from the subscripts on the stress and on the strain. So the first 2 subscripts on the S, 1, 2, 1, 2, 1, 2, 1, 2, and so on, are determined by the strain, which is a subscript 1, 2. And the subscripts, second pair of subscripts, the ones that we call KL, are determined by the subscripts on the S, on the stress. So it's S1, 2, 1, 1, sigma 1, 1, 1, 2, 1, 2, 1, 3, 1, 3, 2, 1, 2, 1, 3, 3, 3, 3. So every strain component, again, is dictated by 9 stress components. And that's a lot to do. And now we want to talk a little bit about what goes into these terms Sij, Kl, and Cij, Kl. The compliance and the stiffness tensors. All right, so what can we say about them? Well, I'm going to write them they're fourth rank tensors. I'm going to write them by indicating two little bars above the S and above the C to indicate that they're fourth rank tensors. They're arrays that are 3 by 3 by 3 by 3. That means they're four-dimensional, so I'm not going to draw it for you. And if you multiply that out, it means that they contain 81 terms. So there's a lot of bookkeeping that's going to go on to try to get coupling between stresses and strains in a three-dimensional universe. S, again, is called the compliance tensor, and it expresses strains in terms of stresses. The C is a stiffness tensor. It expresses stresses in terms of strains. And hopefully this hasn't escaped you, but there is this kind of interesting point that we use S for compliance and C for stiffness. And that's because those words came from the French. And the French, I think, love the fact that Americans get confused by this, that S, the symbol S doesn't go with stiffness, it goes with compliance, and C goes with stiffness. So you have to kind of keep that in mind. Okay, and we've talked about stresses and strain relationships already in terms of the Young's modulus. And so the Young's modulus here, E, is a stiffness, and 1 over E is the compliance. And so we might write the strain as equal to the stress divided by E, or we could equally well have written that the stress is equal to the strain times the Young's modulus E. Okay, well, it's tough to deal with tensors with 81 components in four-dimensional space. And so there's a trick that you can use, and it's called the Voigt notation, or sometimes called contracted notation. And the trick is to use this to take advantage of the symmetry in the crystals and symmetry in these tensor, fourth-rank tensors, to reduce the 81 terms down to 36. So one can show that Cijkl is equal to Cjikl, and Cijkl is equal to Cjilk, and you can read those slowly at your pleasure. And if you do take advantage of that symmetry, you reduce the 81 components down to 36. And then the Voigt, or contracted notation, works the following way. You take your tensor in the normal notation, sigma 1, 1, sigma 1, 2, sigma 1, 3, and you contract it into taking two indices, subscript indices, and replacing them by 1. And the way you do that is you can take the stress tensor and you go down along the diagonal and then up along the side and then over to the left, as shown here by the arrows. And you call them sigma 1, sigma 2, sigma 3, 4, sigma 5, sigma 6. And so what I've done is I built this contracted notation arrangement where 1, 1 becomes 1, 2, 2 becomes 2, 3, 3 becomes 3, and then it becomes less intuitive, and it really helps to think about this form of the tensor when you try to remember where 4, 5, and 6 go. But 4 is here, the first one coming back up, 5 is there, and 6 is there. So following this path is a useful way to remember how to exchange two indices for one index. All right, if you do that, the cool thing that happens is that you can take the 3 by 3 stress and strain tensors and write them as 1 by 6 or 6 by 1 vectors. And you can write the stiffness and compliance tensors, which are 3 by 3 by 3 by 3 matrices. They're fourth order or fourth rank tensors. And you can write them as a 6 by 6 matrix. And that has the following appearance. Here's my stress tensor, written out as a vector, 6-component vector. Here's my strain tensor, written out as a 6-component vector. And here's my, in this case, stiffness tensor that links the two. Okay, and the only thing you have to realize is that there's one subtlety. If you do this carefully and correctly, is the sigmas look okay. It goes sigma 1, 2, 3, 4, 5, 6. But the strains have this little hiccup in them in that they go strain 1, strain 2, strain 3, and then it's 2 times 4, 2 times strain 5, and 2 times strain 6. And that's just a result of about 6 pages of mathematics that will not be shown today. Okay, so now you can do one more sort of simplification to kind of get this into terminology that I think you're all comfortable with, and that's to look at the off-diagonal elements, or to look at what are the shear terms in the tensors. And those are the terms we've written out before in an earlier video. We talked about the shear strain gamma. We showed that it was equal to twice the epsilon ij term, and that the shear stress sigma ij for I not equal to j we wrote out as tau. So that's tau is the shear stress and gamma is the shear strain. And if I rewrite the stiffness and compliance tensors in that form, then I have sigma 1, 1, sigma, tau 4, tau 5, and tau 6. And on this side, I get rid of the 2's that appeared in the strain term before. And so it becomes epsilon, epsilon, epsilon 3, and then gamma 4, gamma 5, gamma 6. And now I could write out the strain in terms of the compliance tensor, the S's. And it simply is S11, 12, 13. But then there are these 2's that crop up if you're careful about how you do your math. And there are some 4's sitting down here. But outside of that kind of 2's and 4's, they have a very simple form where you have a 6-component vector for stress, a 6-component vector for strain, and a 36-component tensor that sits in between. But life is good. You can get away with even more than that if you take into fact that there's energy conservation and deformation can be reversible. Then you can show that, for example, that Cijkl is equal to Cklij. And that takes the 36 components and reduces them down to simple 21 components. So life is getting even easier. We have 21 components. And so if I look at in this case, the stiffness matrix, it's symmetric. And so I've shown arrows to show connections between the symmetric terms. And so the only 21 terms I have to worry about are those that lie inside of this triangular shaped region. And the ones that lie below, down in this lower part, are simply repetitive. So I have 21 going down the diagonal, coming up, including the terms that sit inside that box. And the trick then for most problems we're going to look at isotropic materials, materials that have the same property going to the left as going to the right and going up and going down. And if you do that, isotropic materials only have 2 elastic constants, so the 21 become 2. And in much of what we talk about, we often talk about 4 different elastic constants. We have Young's modulus, which we've talked about in class already, but it's simply if I pull on this inner tube and I apply a certain force, I want to measure how long it gets. The coupling between that force applied or stress applied and the response strain is called the Young's modulus. The shear modulus, it's not going to show you the modulus, but the shearing effect is that if you shear a deck of cards in that sense, the shear stress is my hand pushing on the top card, and the shear strain is the angle through which the deck of cards is distorted. Now clearly this is not an elastic material. If I push the cards there, they don't pop back, but it is a good example of a fluid under shear stress. And then we have Poisson's ratio, which is often used in talking about elastic terms, and so I get elongation, but the other thing that happens is that tube gets thinner. So I make it get longer, but it also gets skinnier in this direction. And that ratio of skinniness to elongation is what's called Poisson's ratio. So it measures how much thinner something gets relative to how much longer it gets. Or if I compress it, how much fatter it gets in this dimension as I compress it relative to how much shorter it gets. And that's a term called Poisson's ratio. So I've just shown you 4 different moduli: Young's modulus, shear modulus, Poisson's ratio, and bulk modulus. But I've told you that there are only 2 independent components. And so these 4 must be related to each other. And there are many ways you can relate them. And I've written down 4 examples down here. You can write, for example, the shear modulus in terms of Young's modulus and Poisson's ratio. Or I can write Poisson's ratio in terms of Young's modulus and shear modulus, and so on. And the final modulus I need to worry about is what's called the bulk modulus. And it's the thing you get if you take a ball and you go down the bottom of the swimming pool, or better yet, take a balloon and you watch it get compressed as you go down, and the pressure of the water compresses it. So it's the response of an object to a hydrostatic pressure. And the other great example, of course, is, as you all know, if you go to the center of the Earth, the pressure gets to be very high. And that's because of all the rocks standing on top, and that causes a hydrostatic pressure, a pressure that pushes in equally from all directions. And the response that you get, the ball gets smaller as the pressure goes up, and that response is described by this term called the bulk modulus. Okay, and I've written out some typical values for moduli here for dunite. Young's modulus is a couple hundred gigapascals, shear modulus is around 80. The bulk modulus is around 130 gigapascals, and Poisson's ratio for many, many, many rocks is about a quarter. And for fluids, the Poisson's ratio is a half, and that's a concept we'll return and talk about more later in the course. Okay, so let's return to linking the stress tensor to the strain tensor. And just as kind of a practice, it's really useful just to kind of do one example of how you now use this 36 or 21 component stiffness tensor or compliance tensor to link stress and strain. So here we are. We're going to calculate components of the strain vector, or strain tensor, in terms of components of the stress tensor. And the piece that sits in between is called the compliance tensor. And I've written it out in terms of the elastic constants that we've just talked about, in terms of Young's modulus, Poisson's ratio, and the shear modulus. So let's take an example. Let's calculate epsilon 1,1, strain, the normal strain in the one direction, in terms of all the stress components, all 6 stress components, and the various elastic constants that sit in between. And so again, we can take this rho in the stiffness tensor, think about rotating it through 90 degrees, and multiply the 1 over E times sigma 1,1. Get the first term. The minus Poisson's ratio over the over the Young's modulus that multiplies by sigma 2. We get the second term, and then a similar term for minus Poisson's ratio over the Young's modulus times sigma 3. And that gives me the strain that I get. And the rest of the terms go away because of the zeros out here. 0, 0, 0, multiply tau 4, tau 5, and tau 6. And so there's some shear stress terms, but they all disappear because there is no elastic modulus that couples in. And one important point to kind of keep in mind is that we calculated the influence of normal stresses, and we found that it produced only a normal strain. Okay, so in an isotropic material, we always only get from normal stresses, we get normal strains, and normal strains couple back to normal stresses. So let's do one more component. Let's do one of the shear components in this vector, strain vector. And so let's calculate gamma 5, and we take the 5th row down in our compliance tensor, rotate it through 90 degrees, multiply it by the stress terms, and we end up with only one term that's non-zero, and that's the term that arises from tau 5, and it's gamma 5 is just given by tau 5 divided by the shear modulus. And we should also note, importantly, that the shear stress and shear strains are only coupled to each other. There are no normal stresses produced by shear stress, or no normal strains produced by shear stresses, and just like there are no shear stresses produced by normal strains. Okay, so normal goes with normal, and shear goes with shear, as long as the material is isotropic. If it's not isotropic, you can couple those two in some very interesting ways that we'll talk about in class later on.